Attributes of polynomial functions. So a polynomial is the sum of, or difference of many monomials. So for example, here's a monomial. I can do the sum of another monomial. I can do the difference of another monomial. These make up a polynomial. It's the sum or difference of many monomials. That's what a polynomial is. The highest exponent of a polynomial is called the degree. So for example, this is a fifth degree polynomial because the highest exponent is a 5. Some people also call that a quintic. Quintic. I'll show you later. Okay, standard form. Standard form of a polynomial. Make sure your exponents are in decreasing order. So notice this example I gave you, the highest exponent came first, then the next highest, then the next highest, and so on. Okay, so let's do an example really quick. I'm going to let you guys do example number 10. Put those in standard form. Ready, go. You can also do these bottom examples. For number 11, let's just let A be the variable. So if I make A be the variable, A that has the highest degree is this one right here. This A value has the highest degree, so that will go first. The next highest A is this one, so I'm going to put this one next. The next highest A is this one. And negative B squared can go last. That's your constant. This represents some number. Okay, for number 12, we can let Y be the variable. So I'll let you guys finish examples 10 and 12. Because this doesn't have an A. So that's why it goes last. It's like A is your variable. So whatever doesn't have a variable, just put it last. Okay, for number 10, y'all should have gotten, check up here, make sure you did it correctly. The fifth degree should have gone first. Next is the third degree. Next is 1/4 k squared, then plus 8k, then minus 1 because this one doesn't have a variable on it, so that goes last. Okay, whatever doesn't have a variable goes last. All right. So let's go ahead and move on. Now we're going to talk about polynomial classifications. So before we start, we're going to talk about the degrees. When you do not have a degree, when your degree is 0, that means it's just a constant. A constant is just a number. So an example of a constant is like 14. That's a constant. If the degree is 1, that means it is linear. You dealt with linear functions a lot in Algebra 1. That's just anything with a single x. So 2x plus 1, this is a linear polynomial. Technically a linear binomial because it has 2 terms. Okay, degree 2. We call anything with a degree 2 quadratic. This is x squared. So an example could be 3x squared plus 4x minus 1 or plus 1. This is an example of a quadratic. Degree 3, that's called a cubic. So anything with the highest degree being a 3. Fourth is a quartic. Although when I look at textbooks and stuff, They normally don't call it quartic, they'll just say fourth degree polynomial. So you'll see it both ways. The technical term is quartic. Fifth degree is quintic. But oftentimes people will just say fifth degree polynomial. So this is fourth degree, fifth degree. Okay, number of terms. If it's just one term, it's a monomial. 2 is binomial, 3 is trinomial. And if it's 4 or more, it's a polynomial. Poly means many. Polynomial. All right. So let's try number 13 together. Looking at the degree, is this constant, linear, quadratic? What is this one? Yes, it's linear. It just has a single x, so it's linear. And there's 2 items, which makes it a, yes, so this is a linear binomial. I'll do one more with you. How about number 18? What degree is this? It's quartic or fourth degree. I feel like most textbooks say fourth degree. I feel like. Maybe I'm wrong. But it's a fourth degree. And is this a, what's the term? Monomial, because there's only one item, one term. Monomial. All right, I'm going to let you guys do these examples and then we'll move on. Now let's talk about parent functions. A constant is y equals some number. I'll just put c. Can someone give me an example of a number? 2. So y equals 2, you just go to 2 on the y-axis and draw a line through it. So that's an example of a constant function. Here is an example of a linear function. Actually, we're doing the parent function. So this is y equals x. And it's just a diagonal line going right through the origin. Your quadratic is y equals x squared. Your exponent is a 2, degree 2. This will look like this. And I'll just give you a hint. When your degree is even, such as 2, 4, 6, 8, 10, it's going to pretty much look like this. So that means this quartic, y equals x to the power of 4, will look very similar. It'll be a parabola shape. These shapes are called parabolas. So please write this little note on your page. When your degree is even, you will have a parabola shape. Okay, when you have an odd degree, y equals x to the power of 3, 3, 5, 7, 9, it's going to look like this. So will this one. Y equals x to the power of 5, it will look like this. With the exception of y equals 1. Y equals 1 kind of looks like that. It goes from the bottom to the top, but it's a little bit different. It's not curvy. Interesting. All right, so these are your parent functions. Okay. So let's talk about the different parts of your parabola. An important part is your turning points. So notice, follow my pen here. It starts increasing, and then right here at the top of the hill, it starts to decrease. This is your turning point. It's decreasing, and then right at the bottom, it starts to increase again. This is another turning point. So let's talk about these turning points. If the turning point is higher than any nearby points, so this point is the highest point in this area, it's called a relative maximum. If your turning point is lower, like this one right here, if it's lower than the stuff around it, in this area, it's the lowest point. What do you think it's called? Yep, relative minimum. The maximum and minimum values are called local extremas. And local because we're just talking about this area. This is the relative minimum. This is the relative maximum. We're not saying this is the maximum point overall. We're just saying it's the maximum point in this little area, okay? And we call this local extrema. Okay, so now let's look at increasing and decreasing points or areas. So let's talk about where the graph is increasing or decreasing. So let's look at this first example. This is your function up here. Notice your degree is 3. That's odd, so it's going to look similar to what we drew earlier. Okay, it has all this other stuff behind it, so it turned a little bit wavy, but it has that general shape. Okay, so this is our graph. Notice right here, what is this called? Yes, it's your turning point. It's your relative maximum. So guys, go ahead and write on your paper your relative max is, we can just round this number. It's 0.7 and 4.3. 0.7 comma 4.3. That is the point of your relative max. Down here, we call this our relative minimum. I'll just put MIN for short. And we can just round those points. I know those are a lot of numbers. So I'll just say 3.3. I'll round to the nearest tenth. And this is negative 4.3. Okay, now let's talk about increasing and decreasing intervals. Okay, so let's first talk about where it's increasing, since this graph starts increasing first. Whenever, please write this down. For increasing interval and decreasing interval, I want you guys to write domain. You need to think about the domain. So write think domain. You should be thinking about the domain when you're answering increasing and decreasing. Domain, you're thinking about your x values, okay? Domain, you're thinking left to right, left to right. So guys, increasing, it starts here on the left and it stops right here. That's where it's increasing. So for increasing interval, I'm going to put on the left, it's at negative infinity. On the right, it stops increasing right here at the x value, 0.7. That's your increasing interval. Think domain. 4.3 is not a part of the conversation. Negative 4.3 is not a part of the conversation. We're thinking about x values, domain. Okay, now let's continue. From here to here, your graph is decreasing. That is between the x values 0.7 and 3.3. That's where it's decreasing. So for decreasing interval, I'm going to say it's decreasing from 0.7 to 3.3. Close the parentheses. Okay, now let's talk about the rest of the graph. It's increasing again. So I'm going to put a little union symbol, and it's increasing again from this x value, and then it goes forever to the right. It's going this way to the right. So that is 3.3, 3.3 to infinity, since it's going to the right forever. That's how you do increasing and decreasing. Okay, let's move on to another one. Next example, I'm going to skip to this one. This is your middle one. Oh, flip it over. Okay, so we have our function up here. Is the degree even or odd? Even. Your degree is even. The highest degree is a 4. So it's even. That means they're both going to face the same direction. Either both up or both down. Okay, so relative maximums. This is a maximum, a relative maximum. That's 0, 5. Relative minimum, we have 2 this time. This is the lowest point in this area. This is the lowest point in this area. So we have two relative minimums. You can just round. I'll do negative 1.8 and negative 3.3. And the other one is around 1.1 and 2. I'll just round this to 3. So those are your relative maximum and minimums. Now I'm missing increasing and decreasing. So let's add that. Put increasing and decreasing, and we'll add that in. And we'll talk about end behavior last. All right. So you're increasing. It's only increasing from here to here, and then from here to the end. So between here and here, your graph is increasing. It goes up. That's between this x value and this x value. So that is negative 1.8 to 0. Remember, you're only looking at x values. So these y values do not matter. Okay, and then it looks like we're increasing again from here to infinity. So that is 1.1 to infinity. That's where you're increasing. Now let's see where you're decreasing. All right, let's see. Oops. You guys try to do the decreasing, and then I want you to look up here. Write on your paper what the decreasing interval is. Ready, go. All right, decreasing. So it's decreasing from here, and then it's coming down to here. This is where it's decreasing. So on the left, you have an arrow. It goes off of the page. That's negative infinity. And here, the x value is right here, negative 1.83. That's your x value. So I'm going to write that down. Negative infinity to negative 1.8. That's where it's decreasing. All right, and then it's decreasing again from here to here. It's decreasing, it's going down. That's between the x value 0 and the x value 1.1. I'm going to round this to 1.1. So that's 0 to 1.1. That is the decreasing interval. Okay, end behavior. This says as x goes to negative infinity, that means as x goes to the left. As x goes to the left, as it goes to negative infinity, what's happening to your graph? So look, as I go to the left, where is your graph going? It's going up. As you move to the left, it's going up. So your graph is going to infinity. As x goes to infinity, so as x goes this direction, what's happening to your graph? It's going up to infinity. So that's how you do end behavior. So really quick, what if I gave you a different graph? Let me just make something up, and I want you guys to tell me what the end behaviors are. So pay attention to what I'm doing in red. Let's say your graph looks like this. Okay, so let's answer this question now. As x goes to the left, what's happening? It's going up still, okay. And as x goes this direction, what's happening to your graph? Yep, it's going down. So that's also negative. That's now negative infinity. Does end behavior make sense? Okay. Okay, for this example, you should have put odd because your degree is 3. It's cubic. Okay, your relative maximum is right here at 2, 4. Your relative minimum, you should have put 0, 0, and that is it. I had a lot of questions about this x-intercept. Relative maximum, minimum, you're only looking at turning points. This is not a turning point, so we won't include that x-intercept. This went down, and it's still going down. It didn't go back up, so that's not a turning point. This is a turning point because it's going down, and now it changes, it's going up. You see? Okay. All right, so now let's talk about the end behavior here. Your end behavior, you should have put, okay, end behavior. As you look to the left, as x goes to the left, what's happening to your graph when you move to the left side? It goes up, so that's infinity. As your x's go to the right, what's happening to your graph? It's going down to negative infinity. All right. Also, you were supposed to do increasing interval and decreasing interval. Okay, so if I start over here, you have an arrow, guys. You have an arrow on the left-hand side. That means it's a negative infinity. And I'm sorry, that's for decreasing. It's decreasing from negative infinity. And then it continues to right here and it stops decreasing. So that's the x value 0. Okay? At 0 to 2, you see it's going up. That's increasing. So from 0 to 2, it's increasing. Remember, you're not paying attention to the y values. You're looking at domain when you're doing increasing and decreasing interval. Finally, it's decreasing again. So at 2, it starts decreasing. It starts decreasing at 2, and it just keeps going to the right. Guys, I'm on the right. You should not have put negative infinity. You should have put infinity. We're going to the right. Yes, it is going down, but remember, we're talking about left and right. Domain is left and right. If you go to the right, notice these x values. They get bigger. This is 6, this is 7. It's getting bigger to the right. So that's infinity, not negative infinity. All right, y'all are doing very good on this explore activity. Let's make sure we're on the same page. When you sketch these graphs, this is a quadratic. This is when the leading coefficient is negative. You can imagine a little 1 right here. So your coefficient is a -1, so it's facing down. Here, it looks like this. You have a negative in the very front. Your coefficient is negative, so it looks like that. These look like that. And these look, sorry, I drew this one the wrong way. Start on the left, go to the right. Okay, so let's answer these questions. It says, which of the functions have the same end behavior on the right side of the graph as well on the left side of the graph? What did you guys say? Which one of these have the same end behavior? E, yes. E has the same end behavior because this side is going to infinity and this side is going to infinity. What else? Yep, A. This one is infinity to infinity. What's this one? They're both going down to negative infinity, right? They have the same end behavior on both sides, and also F. These both have the same end behaviors on both sides. So you should have put A, B, E, and F. These graphs have the same end behavior. What did you guys notice about the degree for these? They're even. So they are even. A, B, E, and F are even. So guys, remember, if you have a polynomial to the even degree, they're going to be facing the same way, either all up or all down. That means your end behaviors are going to be the same, okay? Degrees are even. That means your end behaviors are the same. Okay, so how does the degree affect the end behavior? We just said this. If the degree is even, what do you know? Yep. End behaviors are the same. Same thing again. Okay, number 4, it says, for which of the functions that you identified in question number 1 does the end behavior decrease without bound on both sides? Which one did y'all put? Yep, this is correct. This one decreases without bound. Look, they're both facing down and they go down forever. This one is also facing down. Both sides are facing down. They go down forever. So that's B and F. Okay, let's go on to the next slide. For question number 5, what is true about the leading coefficient of each of these. So guys, what do you know about the leading coefficient here? Yep, that's why they're facing down. So they are negative. Okay, so how does the sign affect the end behavior? It'll basically be the opposite, correct? So for this one, guys, the end behavior was infinity and infinity, but when you put a negative, it just made it the opposite, negative infinity and negative infinity. Let's look at this one right here. As you go to the left, what happens? It's going down to negative infinity. As you go to the right, what happens? Positive infinity. But look, when you put a negative in the front, you see how it's opposite now? This side is now infinity. This side is now negative infinity. Okay? So what you guys should be putting for here is if the leading coefficient, leading means the one in the front. Coefficient, that's just a number. The leading coefficient. This is the number in front. That's what that means. If the number in front is negative, if leading coefficient is negative, end behavior changes. And behavior changes. So guys, the goal of this lesson is that you will be able to figure out what the end behavior is without looking at the graph. Let me give you an example. If I give you this, x cubed plus 4x squared minus 70. I have no idea what this looks like, but I know it's going to look something like this. You can tell me the end behavior. I know it looks like this because it's a 3 cubic. If I give you something complicated like this, negative x to the power of 4, what comes next does not matter. What matters is what's in the very front. It's even, so I know it's going to face the same direction, and there's a negative. It's facing down. It's going to look something like that. I can figure out the end behavior. Make sense, guys? That is your goal for this lesson. You should not have to look at graphs to figure out end behavior.